Our next reaction is addition of cyanide. This is a very old school reaction. It's from classical organic chemistry. It was extremely important in some carbohydrate chemistry in the early 1900s. It's probably less important today, but it's kind of just hung on as a legacy. It does form a carbon to carbon bond, which makes it very useful for synthesis. Our observed reaction looks like this. We're going to start with our ketone. We're going to put in hydrogen cyanide gas, and we're going to add a very small amount of potassium cyanide, catalytic amount. At the end of the reaction, what we will observe is that the cyanide, the C triple bond N, will become bonded to the carbonyl carbon. The C double bond O will be now a single bond, and the oxygen will be protonated. And this molecule is called a cyanohydrin, which stands for cyanohydroxyl containing molecule. The mechanism of this is pretty straightforward. The cyanide is a pretty strong nucleophile, so it first adds to the carbonyl. That puts a cyanide attached, and it breaks the double bond into a single bond and an O minus. Then, because we have a large amount of hydrogen cyanide, which is a moderate strength acid, the oxide here can remove the hydrogen from hydrogen cyanide. That's going to create another cyanide minus, which can then go react again. So that's why we only need catalytic amount of cyanide minus. It reacts, it's consumed, but then gets regenerated. One of the interesting things about cyanide formation is that it is readily reversed by treating that cyanohydrin with base. This just occurs because of the properties of the tetrahedral intermediate. If we put in base, it deprotonates the OH hydrogen. That makes an O minus, which has electron pressure. And it turns out the cyanide is a good enough leaving group that we can push down and push out the cyanide. This turns out to be pretty hazardous because cyanide and hydrogen cyanide are very, very poisonous. Interestingly enough, there was a very controversial quote unquote cancer drug in the 1970s that utilized this mechanism to kill cells. If you're interested in it, send me an email or come talk to me about it. I can tell you a little bit more about this story. Next reaction we're going to look at is called the Wittig reaction. Wittig was a German scientist, and turns out in German, although I don't speak German, but in German, W is pronounced V. So that's why we call it Wittig, but we spell it with a W. By the way, a lot of people in the United States call it Wittig, which is technically not correct, but if you hear somebody saying it, you can understand what they're talking about. So, in this reaction, we start with a ketone or aldehyde, and we react it with this complicated molecule. I'm going to show you how to make this down below. This molecule has a carbon attached to a CH with a lone pair, CH negative. That CH is bonded to a phosphorus, which has 3 phenyl groups attached. So the phosphorus, it turns out, has 4 bonds. When we look, phosphorus would like to have 5 electrons. When it has 4 bonds, it turns out it only owns 4 electrons. It's going to have a positive formal charge. And actually, a key characteristic of this is this positive phosphorus adjacent to the negative carbon. The positive charge stabilizes the negative charge on carbon. This molecule is an example of what's called an ylide. I'll mention that again later in the notes. An ylide is a molecule that has adjacent, opposite formal charges. Now, one of the things that we observe then, if we go and look at the chemistry literature, we can see that a lot of people prefer to write this in a different way. They prefer to write it where they imagine that this pair of electrons has moved down to make a bond between this carbon and the phosphorus. So that would make a double bond. In that case, then, it turns out both of these atoms, the carbon on one side and the phosphorus on the other, would have no formal charge. So they prefer to write it that way. And in fact, I often get lazy and write it that way. The problem with this is that in doing so, as we're going to see in the mechanism, we lose sight of the actual way this reaction is occurring. We really need to have this negative charge, this lone pair, in order to write out the mechanism for this. At the end of this reaction, what we get is the oxygen has been replaced by this piece right here, carbon group, carbon, hydrogen, and there's a double bond between the carbon and the original carbonyl carbon. So this is an awesome way to make double bonds. Okay, let's take a look at our mechanism. Now, to make this mechanism easier to understand, I'm going to use a new symbolism that you haven't seen before, but that's very often used in advanced organic chemistry. And that is, instead of writing pH to represent a phenyl group, instead, organic chemists use the symbol phi, or phi. This is a Greek symbol, okay? Stands for P. One of the reasons why this is useful is that if we look at PPH, it can begin to get very confusing because this P is an actual phosphorus atom. Symbol is P. This P is part of pH, the phenyl group representation, right? And there's 3 phenyls. So in order to make sure that we don't lose the phosphorus, we write Phe, so that now our Grignard reagent becomes R, carbon negative, phosphorus plus, Phe3. I sometimes call this P-Phi3. All right, so what's going to happen here? Well, you can see we have a negative charge. We have something that could be a nucleophile. We know that carbonyls have partial positives. We're going to make a bond between our negative nucleophile and the carbonyl carbon. And of course, to make room for that, we're going to push a pair of electrons out of the way. That's going to give us this intermediate. Now, I drew this carbonyl a little bit differently because what I want to do is I want to put this carbon here, right there. And I want to be able to put the phosphorus up parallel to the oxygen. So what we have in this molecule is very interesting. We have an oxygen negative, and then very close by we have a phosphorus positive. Now, phosphorus has 2 characteristics that are super important for this reaction. The first is that phosphorus forms extremely strong bonds to oxygen. And so if we can make a bond between an oxygen and a phosphorus, that turns out to be very, very advantageous. The other thing is that phosphorus is a 3rd row atom. So it can have an expanded octet. It can make more than 4 bonds. So this oxygen negative, because it's very close to this phosphorus, can just take one of its lone pairs, can just lean across this space and make a bond to that phosphorus. That gives that phosphorus 5 bonds. In other words, an expanded octet. But it turns out, because it's 3rd row atom, that's allowed. So we get this intermediate. And this is a crazy intermediate if you look at it. It's got a 4-membered ring, which we know as ring strain. In the 4-membered ring, there are 2 carbons. Okay, fair enough. There's an oxygen. We'd seen that. And a phosphorus. So a very complicated substructure here. Now, we know 4-membered rings have ring strain. They'd like to break apart. We also know that phosphorus has a really strong bond with oxygen, so it's not just going to let go. So what happens here is really interesting. The molecule breaks apart in the opposite direction from the way that it came together. In other words, the oxygen breaks off of the carbon, the phosphorus breaks off of the carbon and gives the carbon piece the rest of its electrons. So we get a pair of electrons coming up here onto oxygen, a pair of electrons coming down here from phosphorus in between the 2. So if we look down here then, they've sort of separated apart. On this axis here, we get phosphorus plus O minus. This is called triphenyl phosphine oxide. It's a very, very stable compound because of the strong oxygen to phosphorus bond. It probably provides the potential energy driving force for the reaction. And then we get carbon to carbon double bond. Now, one of the great things about Wittig reagents is that we can make Wittig reagents with a wide variety of carbon groups, which therefore means we can make double bonds, which have a wide variety of different carbon skeletons. In order to do that, we're going to use this sequence. So we're going to start with carbon group we want, CH2, halogen. Halogen is going to be chlorine, bromine, or iodide. Again, chlorine is going to be the least reactive, iodide is going to be the most reactive, but sometimes cause problems, and bromine is usually sort of the Goldilocks choice, just right. We're going to react it with this molecule. This is called triphenyl. Notice I'm using the phi's to represent the phenols. Phosphine, triphenyl phosphine, and it has a lone pair. It's a third row atom. It's a weak base, but not that weak, and it's a really great nucleophile. So what we get is nucleophilic attack on our primary alkyl halide here, SN2 reaction. Make a bond here, push the leaving group out. So we get this intermediate. Now what we do is we treat it with a very, very strong base. To get this to deprotonate, we actually use an alkyl lithium. Remember I talked about how alkyl lithiums and Grignards are very strong bases. The particular one we almost always use is N-butyl lithium. N-butyl lithium. So it's 4 carbons in a chain, minus charge on the end, lithium. You can buy this in bottles, and so we would just buy this, suck it up in a syringe, squirt the amount we needed into our reaction. The negatively charged carbon, extremely strong base, would remove the hydrogen here. Pair of electrons would go onto carbon and be stabilized by the adjacent phosphorus plus. So that's our Wittig reagent. And again, if we look here, we have a stable structure, has adjacent opposite charges, so we call that an ylide. This is not the only ylide that exists. In advanced organic chemistry, there have been several that have been identified, and they do really interesting reactions like this. Our last set of reactions are not going to have mechanisms. They're just oxidation reactions, and they just occur on aldehydes because ketones cannot be oxidized without breaking a carbon-carbon bond. Now, that reaction actually exists, but it's an advanced OChem reaction. We don't need to learn it for our class. So let's look at our aldehyde oxidation reactions. Very quickly, we can use KMNO4. Remember that KMNO4 is an oxidizing agent. And we generally use warm KMNO4, hydroxide, okay, warm basic KMNO4. And then we put in hydronium at the end because when we oxidize this, it forms a carboxylic acid. In base, that would be deprotonated, would do acid-base reaction. In order to get the actual acid, we have to put in acid to put the proton back on. So this makes a carboxylic acid. Aldehydes can also be oxidized by Jones reagent. As we talked about, if we were trying to make an aldehyde with Jones reagent, it wouldn't stop there. It would oxidize all the way up to the carboxylic acid. So the corollary is, if I had an aldehyde and I want to make a carboxylic acid, this is probably a great choice. And it is, in fact. So aldehyde, Jones reagent, carboxylic acid. Finally then, a very ancient classical reaction, Tollens reagent. Now, let's first look at this reaction, and then I'll explain it to you why I'm teaching you this reaction. In this reaction, what we're going to do is we're going to actually use silver +1 ion. Now, we can get this in 2 ways. I've seen this written commonly in one of 2 ways. There's probably many ways to write it, but this should pretty much cover most of the situations you're going to encounter. You can either use silver nitrate with ammonia added, and that's an aqueous solution, so aqueous, or you can use silver oxide. Now, silver has a +1 charge, oxide has a -2 charge, so it'll be 2 silvers with the oxygen, again with ammonia. Really what we're going for here is that we have silver plus 1 ion. Now what happens in this reaction is super interesting. We oxidize the aldehyde up to a carboxylate because in ammonia is a base, so the carboxylic acid is deprotonated. Because it's deprotonated by the ammonia becomes NH4 and it gets a positive charge, so that's the counterion. So we get the carboxylate with ammonium. But really interesting, this actually does an electron-based oxidation reduction reaction. So electrons are taken away from the carbonyl and they're given to the silver. So the silver becomes reduced. Well, when the silver becomes reduced, it becomes silver zero, silver metal. So we actually form individual silver atoms in this reaction. Those silver atoms precipitate and begin to form together to form a larger metal. Okay. And when we do this in a glass test tube, that metal deposits, it actually makes a bond to the glass. So what happens then is that when you deposit metal onto glass, you form a mirror. And so this reaction was often called the silver mirror test. It was a way to see if you had an aldehyde in your molecule in the days before we had IR and NMR, which give us much more direct thing without having to run a chemical reaction, without having to chemically change our unknown substance. So the aldehyde is oxidized, the silver is reduced, it deposits on the glass, and that forms a mirror. And so therefore, what we would do is we would take the aldehyde, we would dissolve it in water, we would add this reagent, we would wait a few minutes, and we would look for the formation of a silvery mirror surface on the glass walls of the test tube. That would indicate that we had an aldehyde that was being oxidized. Silver mirror test. Now, again, this is really old-fashioned chemistry. We don't generally do this anymore. We just use an IR or an NMR. But what we see is on standardized exams and things like that, some of this old-fashioned chemistry is still very fashionable. So this is something you might encounter on a standardized exam. That's the last reaction that we're going to cover for aldehydes and ketones in this chapter. We're going to do another chapter where we look at different ways that they can react later.